myself Kalma, lecturer in mathematics in K.B.N college. Today I am going to teach a topic in abstract algebra, which is a syllabus for the second BSc mathematics students. In this session I am going to teach a topic from a unit 4. Topic is permutation and cyclic groups. First of all, what is meant by permutation? Permutation is a mapping which is defined on a same set and satisfy the 1, 1 and onto property. Here it can be written as permutation is a 1, 1 mapping of a non-empty set onto itself, which is nothing but a permutation is a bijective mapping of a non-empty set into itself. For example, if there is a set S is equal to set of elements A1, A2, A3 and so on An, if the mapping is defined between the set S onto itself, that should satisfy the 1, 1 and onto. That is written as 1, 1 mapping from S onto itself is called a permutation mapping. Here we have the n elements, then we can say that it is a permutation of a degree n. In this unit, we have an important and named theorem, that is Cayley's theorem. This theorem says that a mapping between a finite group and the obtained permutation group, there should that mapping satisfy that isomorphism properties. That is, every finite group G is isomorphic to its permutation group. For that purpose, here we are solving this theorem in 3 parts. In the first part, we define a mapping and we prove that that mapping is permutation. In a part 2, we are going to take all these permutations in a set and we prove that that set is satisfying the group properties. Then the set become the permutation group. In the third part, the main part, we are going to define a mapping between this finite group and the permutation group, and we prove that that mapping is isomorphism. For that purpose, we are taking an element in a finite group G. Clearly it is given that there is a group finite which is G. Let G be a group. Since G is a group, that means clearly there should be a set which is non-empty. So for that purpose, we are taking an element A belongs to G. By using the closure property, we can take another element X belongs to G such that AX belongs to G. By using the closure property, since G is a group, we are writing here AX belongs to G. In a first part, we have to prove that a mapping is permutation. For that purpose, we are defining a mapping FA. To indicate that we are proving for every element in a group G, we are defining a mapping here FA from G to G such that FA at X is equal to AX for every A belongs to G. Now we have to show that this mapping is permutation. From the definition, we have to prove that this mapping is 1, 1 and onto. Here we are defining this mapping. For that purpose, in the first point, we are going to prove that this mapping is well defined. For that purpose, we are taking 2 elements in the set G. Then we get, let X comma Y belongs to G such that X is equal to Y. To prove that this mapping is well defined, we have to take the 2 elements in the set G and we have to prove that their images are equal. For that purpose, we are considering X is equal to Y and these 2 elements are the elements in G. And since G is a finite group, we know that every finite group satisfies its cancellation law. By using that property, we are multiplying an element in the G on both sides, that is A. Then we get AX is equal to AY. From the mapping of the permutation, we can write as AX as FA at X. And similarly, we can write AY as FA at Y. That means if we took any 2 elements in the set G, then their mappings are equal. Clearly, we can say that FA is well defined. Now we have to prove that this FA is 1, 1 and FA is onto. First one, what is FA is 1, 1? How to prove that FA is 1, 1? Taking the images with the mapping FA at X is equal to FA at Y, we have to prove that X is equal to Y. That is, if images are equal, then we have to prove that elements are equal. For that purpose, we are taking an L2 elements X comma Y in the set G. From the mapping of the permutation, we are considering FA at X is equal to FA at Y. By the mapping, we can write as FA at X ax. Similarly, we can write fa at y as ay. By using cancellation laws, we can write ax equal to ay as x is equal to y. In this part, we proved that if the images are equal, then the elements are equal. If it satisfies this property, then the mapping is said to be 1, 1. Now next one is onto. First of all, what is onto? For every element in a domain, there should exist an element in codomain with the mapping. For that purpose, we are taking an element x in the codomain G. In the domain, we are taking an element A inverse x belongs to G. Let's see how it comes. Since G is a group and A is an element in G, then since G is group, that means it satisfies the existence of inverse. By that property, we can also write that A inverse belongs to G. Already we have an element x belongs to G. Now we get an element A inverse belongs to G. By using the closure property, we can write A inverse into x belongs to G. Therefore, A inverse x belongs to G in the domain. Now considering the mapping Fa at A inverse into x. By the mapping of Fa, we can write Fa at x is equal to Ax. Here in place of x, we have A inverse x. Then we get A into A inverse x. Since A inverse and x belongs to the set G and G is a group, then with the second property of a group associative law, we can write A into A inverse x as A into A inverse into x. Also G is a group. By the existence of identity property, A into A inverse can be written as E and E into x can be written as x. Therefore, if A at A inverse x is equal to x, that is, for every element in a domain, there existing an element in a codomain with the mapping. That is, for every A inverse x belongs to G, there exists some x belongs to G such that Fa at A inverse x is equal to x. Hence, the mapping Fa is onto. Previously, we proved that Fa is 1, 1 and Fa is onto, and the mapping Fa is from the same set G to G. Therefore, Fa is a permutation of G. Now, taking all these permutation mappings under a set G dash, that is defined as, let G dash is equal to set of Fa such that A belongs to G. It is a set of all permutations which is obtained on G. Now to prove that this G dash is a group. For that purpose, we have taking a binary operation dot. That means in a part 2, we are going to prove that G dash comma dot is a group. In G dash, we all have that all the permutations defined on. To prove that G dash is a group, first of all, we have to prove the closure property. Since the finite group G is satisfying all the properties like closure, associative, existence of and existence of inverse, that means G satisfies the closure law. Here we are using that property. Let A comma B belongs to G such that AB belongs to G. Now we have to prove that G dash is also satisfy the closure law. But in a G dash, we have all the mappings in the format FA, FB, FAB. Now we are to prove that it is satisfied the closure law. We are taking the three elements FA, FB at FAB belongs to G dash. Now considering the FA into FB at x. That can be written as FA into FB at x. FB at x, from the permutation mapping, we can write it as B into x. That means FA into BX. From the mapping of a permutation, Fa at x can be written as Ax, but in the place of Ax, here we have the Bx. Then we get Fa into Bx can be written as A into Bx. Since all the elements A, B, X are the elements in a G and G is a group, it satisfies the associative law. By using that associative property, A into Bx can be written as AB into X. From the mapping of the permutation, A into X can be written as Fa at x. Here in the place of A, we have AB. Then AB into X can be written as FAB at x. Therefore, Fa into FB is equal to FAB. Hence, G dash satisfy the closure property. Now, we have to prove that G dash satisfy the associative property. First of all, G is a group. Clearly it satisfies the associative law, that is, if any three elements A comma B comma C belongs to G, we can write it as A into BC equal to AB into C. Now we have to prove that G dash satisfy the associative property. For that purpose, we are taking here three mappings, that is FA, FB, FC in the set G. Now we are considering FA into FB into FC. Now we have to prove that FA into FB into FC. By the mapping of the permutation, we can write it as FA into FB into FC as FA into FBC by the closure property which have we previously proved. Now from the permutation group, we can write FA into FBC as FA at BC. Now FA at BC can be written as FAB at C. By using associative law, we can changing ABC as FAB into C. Then we obtain FAB into FBC, that can be written as FA into FB into FC. That means here we had considered FA into FB into FC and we proved it as FA into FB into FC. Clearly, it satisfies the associative law. And the third property is existence of identity. Since G is a group, we know that in that set it satisfies the existence of identity. We have an element E. That can be written as, since for every A belongs to G, there exists an identity element E belongs to G such that A into E is equal to E into A. For that purpose, here we are taking an element FA into FE as FAE, which is equal to FA. That means there is an identity element in G. By using that, we are taking an element FE in G dash. That means let FA comma FE belongs to G dash and it's satisfying that FA into FE is equal to FAE, which can be written as FA. Similarly, we can prove that FE into FA is equal to F into EA, which is equal to FA. Clearly, FE is the identity element in G dash and G dash satisfy the existence of identity property. And the last one is existence of inverse. Existence of inverse, since G is a group, by the inverse property we know that A inverse belongs to G. But now to prove that G dash satisfying the existence property, we are taking the two mappings, that is FA and FE in the set G dash. Also G is a group, then we can clearly say that A inverse also belongs to G. For that purpose, we are considering FA into FA inverse. That can be written as FA into A inverse from the property of closure law, which can be written as FE. Therefore, FA into FA inverse equal to FE, which can be written as FA inverse into FA. Clearly, here FA inverse is the inverse element of FA. Hence, G dash satisfy the inverse property. Previously, G dash satisfy the closure law, associative law, existence of identity. Now it proved that G dash satisfy the existence of inverse property. Hence, G dash is a group. But G dash is a set of all the permutations. Hence, G dash comma dot is a permutation group. Hence, we can say that the algebraic structure G dash comma dot is a permutation group. The main theorem we can be proved in the part 3. That is, already we have the set finite group G. Now we get the set G dash, which is its permutation group. Now we are defining the mapping between this finite group and the permutation group G dash, and we have to say that this phi satisfy the isomorphic properties. That is, we have to say that this mapping phi is 1, 1, onto and homomorphism. For that purpose, we are defining a mapping phi from G to G dash such that phi of A is equal to FA for every A belongs to G. Now step by step we are going to prove that phi is isomorphism from the set G onto G dash. First one is phi is 1, 1. First, to prove that phi is 1, 1, we are define the images with the mapping phi. For that purpose, we are taking the elements A comma B in the set G such that phi of A is equal to phi of B. By the definition of phi, we can write phi of A as Fa, which is equal to, similarly we can write that phi of B as Fb. And here Fa and Fb both are the permutation mapping. So considering the elements on both the sides, then we get Fa at x is equal to Fb at x. By the definition of the permutation, we can write Fa at x as Ax, similarly Fb at x as Bx. Since all the elements A, B and X are the elements in the finite group G, and we know that a finite group G always satisfies the cancellation law. By using that property, we are cancelling X on both sides, then we get A is equal to B. That is, if we consider images with the respect to phi, that is phi of A equal to phi B, then we get the elements A equal to B. Clearly we can say that phi satisfies the 1 property. And the second property is, now we have to show that phi is onto. That is, for every element in a group, there exists a permutation in the G dash. We have to prove with the A mapping. That means for every element in G, there exists a mapping Fa belongs to G dash such that phi of A is equal to Fa for every A belongs to G. It is a clear property by defining the mapping, hence phi is onto. And the third property, we have to prove that phi is homomorphism. So for that purpose, we are taking the two elements in the group G. Let A comma B belongs to G such that phi of AB. Now considering here phi of AB, from the definition of phi, we can write as FAB. By using the closure property, we can write FAB as FA into FB. By the mappings of the phi, we can write Fa as phi of A and Fb as phi of B. That means if we consider phi of AB, that can be written as phi of A into phi of B. Hence, it satisfies the homomorphic property. Clearly, phi has satisfied 1, onto and homomorphism. Therefore, phi is isomorphism, and the mapping is defined from the group G onto its permutation group G dash. Hence, phi is isomorphism from the finite group G onto its permutation group G dash, and it is symbolized written as G is isomorphic to G dash. Clearly, this Cayley's theorem says that every finite group G is isomorphic to its permutation group. Hence, we proved the Cayley's theorem. Thank you.